Okay, good afternoon. Right, so we're going to talk about detrital apatite this afternoon, and I just need to acknowledge my colleagues that have participated in this since about 2012 when we started this work, I think. Mao, Alexei Ruklov, Travis Furby, and Adrian Hicken are scientists at the BC Geological Survey, and Jody Spence and Lawrence Coogan are faculty at University of Victoria, or as an adjunct and the chief of the survey. So this group has been together, and I need to acknowledge them. Let's see if this works. Okay, well, this group probably doesn't need to know it, but really, for indicator minerals, which we're going to talk a little bit here the next session, we're really talking about expanding the search area by working under cover. And transported cover, it's exotic or redistributed material of continental origin, and it blankets bedrock or cemented variants of that. And it includes glacial sediments, colluvium, alluvium, and even recent volcanic ash. And you can view it as an opportunity rather than an impediment. I don't like cover, never did, but it hides a lot of really interesting deposits. So if you're clever and you can see an advantage, you can absolutely outwork your competitor. So it's important that we embrace that, I think. These are just some areas. BC has 50% of British Columbia is under glacial cover. And actually most of the great terrains, Stachean, Quinalia, these host all the great porphyry and VMS deposits. And the central part of BC has literally 7 mineral occurrences, advanced prospects, about 13 all up. So it's incredibly underexplored, and that's what we've spent a fair bit of time trying to do. And of course, you've got Mexico down here. This is a Colorado epithermal. You've got a copper skarn, and this is basin and range kind of thing. So you're shedding sediments into the basin that steps eastwards. Of course, down in Chile, we have the same pediments, and we're shedding materials, obviously porphyry origin, into the foots of the basins, the pediment plains. So lots of areas where we can actually think about how we might use detrital chemistry. And of course, West Australia, lots of regolith, and you deal with that here. So resistate indicator minerals. Our objective when we were looking at this is we thought of them all. We find one that works for all types of mineral deposits. And apatite does fill that requirement, I think, better than any of them. What you need is it has to be widespread in rocks related to or within the deposit. So lots of deposits have a variety of accessory minerals. I've worked a long time, and apatite was one that you almost see in most every type of mineral deposit. There's a few it's not, but it's very widespread. Phosphorus is very insoluble, so it comes out of magmas, comes out of the fluids. Composition needs to be sensitive to the crystallizing environment, so it has to actually reflect the PTX conditions of its crystallizing environment. If it doesn't do that, it's not going to be too useful. Has to be resistant to chemical physical weathering, and you have to be able to identify it easily and separate it from its host rocks and sediments. So something like magnetite, very nice to use because it's magnetic, you can pull it out. Apatite is fairly dense, fairly heavy, so it's quite easy to separate in the separation process. So it fits all that, and I should just point out that kimberlite indicator minerals and porphyry indicator minerals, this doesn't work so well, KIMs and PIMs, they've received a lot of attention, and we're now looking at orogenic and IOCG and other deposit types, and apatite actually, we've done that work there. So lots of indicator minerals. I think anything that you can see under the microscope, some aspiring, interested mineralogist has had a go at it. So these are just a whole variety. These are typical PIMs. I think we'll see some more talks today on those. So why apatite? We mentioned it fills all those 4 criteria very well, but also it's just a garbage pail. It has 53 elements of the periodic table can be incorporated into the apatite structure. It's remarkable what this mineral can do. We want it to be a sponge. So initially when you think about this, if you're a petrologist, mineral chemist, you're often looking at tight stoichiometric minerals, so you can figure out exchange reactions that you can relate to pressure, temperature, FO2, something like that. We don't want that with apatite. We want just a sponge that can collect whatever elements are in its environment. So if we're looking at convergent nickel deposits or orogenic nickel, like Agua Blanca, we're going to want scandium, manganesium, vanadium, chromium. Apatite can pick up those. If we simply go to, say, a porphyry, we're in a felsic rock environment, you want light rare earth elements, and a variety. You go to orogenic gold, you're looking at arsenite, pyrite, tellurium, tungsten. So that all those elements reflect their environment. And apatite, unlike, say, magnetite or even tourmaline, is quite a garbage pail, but they don't have the ability to take those elements in to be useful in discriminating. And this is the structure there. A big columnar column contains the anions, and then you've got 2 metal sites, C1, C2, calcium, and then you've got phosphorus in tetragonal coordination. So, and these are much of oxygens. So I just point out that a lot of the work I'll be talking about today, you can download this for free. It's open access. And shout out to the group. It was awarded the 2016 Skinner Award for the best paper in economic geology. You can download the Excel table I'm going to show you. That's all you need to do. Get your elements from ICP-MS laser ablation, plug them into the Excel table, and all the diagrams I showed you are calculated for you. So you don't have to do anything. It's very easy to use. So just before we dive into a little more details on using it, we sampled a global collection. You'll see that mid-ocean ridge gabbros, we collected them from Lawrence Coogan, had samples of these. All the carbonatites, 29 world carbonatites in the green triangles Alexei had. And a lot of the samples came from my own collection in the Canadian Cordillera. Also a few out here, Minyari, O'Callahan's made it in there, CB, Kirkland Lake, a few others. So it's global in nature, but it's focused on the Canadian Cordillera. But there's no reason that the applications and the conclusions from there don't fit in other orogenic belts. Right in BC, just to give you a flavor, we looked at all these types of deposit apatites for all these types of deposits. As I mentioned, we didn't find them in SEDEX or VMS. I haven't seen them myself. I've seen a few. I talked to a bunch of other folks that work on these systems. And then Mike Gadd put a paper out 2016. And apatites in VMS and SEDEX, they're hydrogenous. So they're basically they're reflecting the marine environment. So the composition doesn't vary very much at all through different layers. That makes sense. We didn't see them. We looked for them. Mao spent a lot of time looking at VMS and SEDEX because we didn't want to make any assumptions. And then otherwise, so these are the ones we did. This is also what I'm going to show you today. So once we developed the criteria, we've tested it in a few cases. And this one was published just a year ago, 2018 at Roundup. And it's available at the websites, MAC. It's cheap. It's $60. We priced it very low, $40 if you're a member. But give me an email and I'll flip you whatever the paper. But we looked at 10 areas in central BC, that great covered terrain that has Stikine, Quinella, and I'm going to show you one or two of those right now. And that's more of a manual for how to actually use the technique. So very quick background. We selected apatites, as I mentioned, from many deposit types and unmineralized host rocks. So we looked at 20 igneous complexes and looked at monzonites and cyanites. So we've looked at all the barren intrusive rocks that you're going to find with porphyries and any of these magmatic associated deposits. Most of our mineral deposits we looked at are magmatic associated. There's a few that aren't, orogenic, may have magmas, may not, but most of them have a magmatic signature to them. We analyzed the apatites by laser ablation ICP-MS and the probe. We determined the elemental characteristics, and you can plot these up on rare earth elements and spidergrams. There can be quite illuminating as to what processes you might think be going on in your deposit area. We undertook statistical treatment of the data using discriminant projection analysis in iogas, and then Mahalanobis contouring by Mahalanobis in 1936 he did it. And then from that, we developed an optimized series of discrimination diagrams, 3 steps, to separate apatites into the types of ore deposits and unmineralized rocks. And I just point out that it is a very nice fertility indicator as well for porphyry systems. A paper I just sort of read, a short little abstract, I think Jamie Wilkins and those guys were saying that, we didn't look at unmineralized porphyries. We did. There's 20 of them, monzonites and everything. So we've identified the barren igneous rocks from the mineralizing porphyries and hydrothermal systems. So just point that out. So this is all in Mao, so I wouldn't dwell on it, but why Dpa analysis is very good is it provides an optimum set of rules to classify a sample into one of a set of groups. We predefine them by projecting the multivariate data into lower dimensional space to show the best separation. But unlike PCA, the Dpa uses an a priori knowledge of the group membership to define these rules. So we know that apatite's from Highland Valley. We know that apatite's from Macassa and Kirkland Lake, it's orogenic. We know it's from Olympic Dam. So we have great control on those, and those samples also came from our 120-year-old geological survey library, so we know exactly what veins they're from, and also my own collection. So we have great control over our database. And what this does is DPA calculates these linear discriminant functions that maximize the ratio of the within groups to the between groups sum of squared matrices. So these functions are projections, really. They're linear combinations of the original variables, those are the elements, we used 11, that maximize the difference between the predefined groups, which allow the samples to be plotted in this discriminant space so that you can separate them. So the technique really maximizes the similarities of your data set and really emphasizes the differences between those groups. And when you use Mahalanobis contouring, that is a statistical treatment where you're looking at downgrading the outliers. So instead of having a circle, you'll have an ellipse of the data. So both of these techniques are great if you know the training set of data you're using. So here's what you're going to get. All you need to know, this is an Excel spreadsheet. You download it, your data. You would just enter these 11 elements. We initially analyzed 48 elements, used laser ablation and probe, got it down to 28, and we picked 11 final elements when we looked at the detection limits across all the deposit types, all the carbonatites, all the unmineralized rocks, and looked at what elements were above detection limit and what elements were in best abundance in all those types. And these were the 11 we came up with after we looked at all that. So you just enter those elements in here, and you'll get a score will be calculated, and this is then plotted on these axes. You can see they just plot right on DP1 and DP, see that here, DP2 and DP1. And you'll get a field for mineralized rocks, ore deposits, and carbonatites. Carbonatites is a separate field because apatite is such an important element in that group, and we had 30 carbonatite complexes. There's also a bit of a tectonic thing we've been working on this as well. So you can find, that's the first diagram, and then the actual system, you plot each one of your samples that will plot up in a series of diagrams. And this is just an example of a till sample you would get. There was 11 usable apatites, so we plot them in the first diagram. The first diagram, and it will tell you here, you can see these 11 apatites are all ore deposits. But we also found that if they plot close to the field boundaries, these two additional plots, which allow you to remove the gabbros from mid-ocean ridges and also some granodiorites that plotted close there. So this just re-emphasizes that those ore deposits absolutely plot as ore deposits. If it fell into one of these fields, you'd disregard it. You wouldn't use it further. The first step then is those 11 samples there. They're plotted into this first diagram, which breaks out the different types of ore deposits. And let's look here. You can see that porphyry ores in the PO, iron oxide apatite and IO8 deposits, gold skarns, orogenic nickel, orogenic gold, gold skarns, I think I see that in my eyes here. Tungsten skarns. So if you look at the one circle, look at porphyry ore, you'll see there's the circle there. That plots as a porphyry ore here as well, and also as a porphyry ore here. So that one, once we have a porphyry ore or a skarn, you put it into step 3, and this breaks it up into the different types of porphyries and skarns. And you can see down here you have alkalic porphyry, porphyry copper moly, porphyry moly, gold skarn with other copper skarns in that one, and then we also have copper breccias. Yeah, so I think that's it. It's a little small screen. And then you can see in the case of iron oxide apatite, iron oxide deposits, IOCG deposits, there's one sample that has a triangle, and it, looking here, yeah, so this triangular one, you can see it plots right on the line there, but in the two other diagrams, it plots in the iron oxide classification. So it actually is an iron oxide, and then you take it down to this plot, and it's an IO8, it's carunitite. Why there's a little bit of overlap is this is a three-dimensional, DPA is a three-dimensional volume for those samples. So these are slices through those volumes to best clarify how so you can use it in a two-dimensional, so you can see it two-dimensionally. So that's why we have a series of diagrams that basically show the same fields, but some of the fields are better defined in one of the diagrams or the others. But it should plot in the same, or at least 2 out of 3, that becomes its classification. Okay, so that's kind of the idea. That's how it works. Put it in an Excel spreadsheet, shows you where it should plot. Appendix 2 walks you through that to explain how you do it. You don't just throw all your data up there at once. You can walk it through, and once you've classified it into those ore deposit types, you're done. If it's a porphyry or a skarn or an IOCG, you walk it through the next step. So in 2017, we published this. Well, we finished it off, And we want to trial this in a greenfields exploration program in the Chaco Plateau, doing exactly what a company would do. We just looked at areas of high and low exploration potential based on min-file occurrences, the developed prospects and showings. Geochemical anomalies, so we have a lot of till geochemistry that we're going to show you. And then we also had abundances of detrital, chalcopyrite, and gold, because there was a large study where all this data was collected by Geoscience BC. So we had all the separates, and so we looked in those areas. Okay, perfect. And so I'm just going to show you one area. So we basically, if we go to the Chew area, oops, sorry. The geology here is we're in the early Jurassic Hazelton and Middle Jurassic Bowser group. These are volcanic arc rocks and siltstones and sandstones in the light green and dark green. And then they're intruded by late Cretaceous to Eocene plutons, granodiorite, that's the Chew. And these are more cyanidate diorites, which will play a role in a minute. We don't know their age, but they're probably, we don't know, it could be Cretaceous or Jurassic even. And then we've got Utsa Lake, felsic volcanics, and then we've got these early Miocene basalts. But it's all undercover. So we have projects. The Chew we mentioned is a very well-developed, well-known moly deposit. Ben is another porphyry moly down here. The C is a porphyry moly copper, which also has some gold-silver veins. And then April, which sits right along here, the April fault, is a series of gold and silver veins. Probably, we think, orogenic, could be epithermal. So if you now look at these box plots, these are basically individual apatites that have been classified. So we pulled these out of the tills, we've run them through the classification, and if you see sitting right on top of Chew, you have there's a sample. The sample sites are in the light green. Ice flow directions are in blue, so ice is going that way, so everything is down ice towards the northeast. You see right on top of Chew, most things are all either tungsten skarn, and there's a lot of, this is intruding into a lot of limestone. So we've got a lot of really nice tungsten skarn development in the area. So apatites, we've got a bunch of them from porphyry moly, and then there's one that's a porphyry copper moly breccia, and then there's also a alkalic porphyry apatite. If you go to the next one just above, right here, it's all just porphyry moly and tungsten skarn, exactly what you would expect. And then we go a little bit further out, and you can see this one. It has porphyry, some alkalic porphyry, and it also has porphyry moly and tungsten skarn. This one sitting here, this sample, sitting right in front of the April showing, also C, also has a lot of alkalic porphyry, so it's really suggesting there's something going on with some of these alkalic systems, perhaps. And then we have porphyry moly, and then there's 3 alkalic or orogenic gold as well. Further out, you can even see 8 to 10 kilometers away, we're still getting the porphyry moly and the skarn. So you're going to see in a minute the geochemical anomalies only go out to about 5-6 kilometers. This technique goes 5 kilometers past any geochemical anomaly. If you pick up tills and you look at the apatites, it's telling you that the Chew is at least 10 kilometers away, but the geochemical anomalies drop off far, so it gets you out further. If we now look at moly, and here's the, these are percentiles, 98, 95, 90, and 70 percentiles going from red down to white. You'll see here's the, in molybdenum, it's sitting exactly where you'd expect. There's the the Chew occurrence, Ben is down here, and a very nice moly anomaly. Copper, it doesn't associate with porphyry moly so much, and so we don't see it. We see it's down here more with the Ben and also the C, which is a porphyry moly copper, and that makes more sense that it's a little bit offset. Also, if there's alkalic, that's exactly where you would expect it to be. If we look at silver, we'll do silver, get that back. With silver, you can see it's sitting right along the April fault and down ice of the April fault where we've got those gold-silver veins. And we think they're probably orogenic. The April fault probably goes right from the top. I didn't highlight it right down. Arsenic, same as it's picking up. Sorry, it's picking up the same, I think, these gold-silver veins that are sitting in the April fault. Tungsten, yeah, it's right where you'd expect. It's right on the margin, certainly the margin of the Chu intrusive, where you've got all the tungsten skarns. And we saw those skarn apatite, those tungsten skarn apatites. And then tellurium, yes, we're right down in the orogenic gold area. It's right at this area is where we've got the April showing. And there's a whole series of these little showings. That's just the best known one. But there's gold silver veins all along the April fault. And gold, it's right where it should be. So finally, if you look at geophysics, we had geophysics, it's too coarse grained. It was done as part of the Trek study. It really doesn't show anything, but you can see the hornfells, the more magnetic anomalies. Interesting, if you look at chalcopyrite grain counts, there's only one. We didn't find chalcopyrite grains in the entire study, probably overestimated as an indicator, a detrital mineral. We're in temperate climates, so we never think of sulfides anyway, but they do occur in Canada. But there's a couple reasons why they weather out. So they don't survive transport, they weather away. And they also, if you're looking at, say, porphyry systems, apatite, for example, occurs much more widespread. The porphyry ores are typically deeper, they're more concentrated perhaps in the potassic zone. So when we glaciate these things, we often don't get to the actual sulfide zone. We're still in the alteration zone. So there's a couple of reasons why we don't think we're getting the chalcopyrite as much as we would like in any of these deposits we're looking at. And then finally to the south, here's some gold. And you can see there's a significant number of gold grains that are all up ice of the April fault showing. So it's just showing that basically the geochemical anomalies, the gold grain counts, and the apatite indicator is picking up exactly the deposit, the prospects, and the occurrences that we see. And that was just blind. We just picked those out to do that. So that worked out nicely. So finally, I think detrital apatite successfully identified targets in both greenfield and brownfields. I just showed you 1 out of 10 areas we've gone through. It is a porphyrophilic indicator. It does discriminate between barren intrusions and mineralized intrusions. And then what I think we're going to do now is sort of look at the degree of fertility, because all we can tell you with this, we can't tell you how close you are to the actual mineralized system. It depends on the size of it. Porphyry is going to give you a whole lot more apatites than a skinny little orogenic vein. So you have to think of these things. It's not a black box. You have to look at the size of the system, how many apatites you might get, and then it's not going to tell you, it'll just tell you that alkalic porphyry style mineralization is developed. Whether it's a Galore Creek or whether it's just something the size of this room, it can't tell you that. And apatite's a first cycle detrital mineral. That's an advantage in many ways. And what it means, it's not as robust as, say, zircon or tourmaline. Those will last 3-4 glacial movements. So God help you trying to trace that back in the Cordillera. Whereas apatite, if it's there, it's only gone up ice. It hasn't survived a second cycle. So very effective. And then this is an improvement over geochemical anomalies in till that are non-specific. In BC, we often have SK Creek. They're VMS deposits with great precious metal enrichment. They have the exact same geochemical anomaly as a gold-enriched porphyry. It's base metals, gold, copper, silver. And I've worked on those for many years, and this technique is great because I no longer am wrestling with whether it's an SK Creek or something like a precious metal porphyry. And then finally, I said it's not a black box. So even though these are very, very effective, you have to still think about geological maps or mineral grain counts if you're getting some deposit type that makes no sense. So example, we didn't get any orogenic nickel. Well, we shouldn't, right? If you're getting orogenic nickel and you don't have any ultramafic body around, you should probably, there's something wrong with the grain, and you can look at it. And often there's alteration. You can look at the trace element chemistry, and we talk about in the paper how you can disregard those ones. Thank you very much.